Hello class, in this video we're going to talk about formulas for exponential and logistic functions. Now we're primarily going to be setting up and solving exponential functions. We will be setting up logistical functions, and I guess we'll be solving for certain values along the way. But please refer to this. I don't want to be switching back and forth between all my slides, so remember these formulas will be the ones we'll be using throughout the video. So example 1, the population of Smallville in the year 1890 is 6,250. Assume the population increased at a rate of 2.75% per year. Estimate the population in 1950. So our general formula, there we go, is P times, now it increase, so anytime we're increasing, we're adding our rate to 1. And then usually this is T, okay? So our principal, our starting value was our population. That's another reason why it's good that it's P. So 6,250 times 1 plus, and for your rate, don't forget to move your decimal over 2 places. Always important. And there we go. And then how many years passed between 1890 to 1950? That'd be 25. Now, once you've got it set up, you are expected to do the calculations in your head. Don't reach for a calculator. Make sure you do the work by hand, like I am doing now. No, I'm obviously just kidding. So we get 12,314.75. But we're talking about people here, so we're going to round to the nearest integer, 12,315. And I should be saying approximately, not equal to. Okay. So why don't you go ahead and give the next one a chance. So the population in Las Vegas, Nevada in 2000 was 478,000. It's increasing at a rate of 6.28%. What will the population be in 2010? So 478,000 is our principal. Our rate is 0.0628, and our time is 10. And rounding to the nearest integer, that's approximately 878,908 people. All right, let's go ahead and talk about a substance with an initial mass of 15 grams is decreasing at a rate of 4.6% per day. How much will remain after 1 year? So we are going to work off the decay formula. So instead of a plus here, we're going to do minus, but that's the only change. So the initial amount is 15 grams, 1 minus 0.046. The power of 1, well, no, because this is per day. So we got to think how many days in a year? 365. 15 times minus 0.046 to the power of 365. And that gives you an incredibly small number of, it looks like 6 zeros. 1, 2, 3, 4, 5, 6, and then a 5. So that's tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths, 5/10 millionths of a gram remaining. So basically none of it left. So go ahead and pause the video and give the second one a chance. Okay, so we have another decreasing problem. Okay. Now, with the percentage, be careful. It's 0.59%. You're going to want 2 zeros next to that decimal before you do 59. And it's 1 week, but again, we're talking about per day. So you end up with 4.797 grams. And I probably should have been labeling my answers this entire time. All right, so we're back to Smallville in the year 1890. It's 6,250. Assume the population increased at a rate of 2.75% per year. When will the population reach 50,000? So this time we're using our growth formula. Again, I'll write it out. P times 1 plus R to the power of T. But we're asked, when will it reach a certain population? That's going to go for our A value. That's 50,000. And then everything else will go where it belonged before, times 1 plus 0.0275t. Now, there's some algebra to do here because we're solving for an exponent. So the first thing we're going to do is we're going to take care of that 6,250. We're going to divide it by both sides. So 6,250. 4 zeros divided by 6,250 is 8 equals, and then I'll simplify what's in here, just make it 1. And actually, I'm going to give myself a little bit of room. Okay. 1.0275 to the power of t, because now we're going to take the natural log of both sides. You can do the logarithm of any base. I was up front at the beginning of this unit. I mostly use natural log. So we're going to write out natural log of 8 equals t times the natural log of 1.0275. And let's not forget, now that we've got it in this form, natural log of 1.0275 is a number. It's a weird number. We just think of to ourselves, if we had 2t equals 8, how would we solve this equation? We would divide by 2. It's no different here. It's funny looking, but it's a division process nonetheless. We divide by natural log of 1.0275 on both sides. 1.0275. And I would keep these as natural logs as long as possible, especially when you're doing your homework on My Math Lab. If you do it now, your decimals will get crazy and you might not wind up with correct decimals according to the automatic answer. So doing it this way will reduce any rounding errors. So we're talking about the natural log of 8 divided by the natural log of 1.0275 is 76.65. 76.65. And this is per year, so this is in years, so we can keep it as a decimal. It's going to take about close to 77 years to reach a population of 50,000, assuming it continues to grow at that rate. So go ahead, pause the video, and see what you get for this next problem. Okay, so once again, we're using our growth formula. You can get these as decreasing problems, so keep that in mind. We start with 1 million on this side, 478,000 over here, and then our rate. I divide it by 478,000. Now here's my first tip. When you're doing My Math Lab and it asks you to round to a certain decimal place, we had no choice here. We had to round at a certain point. If it says, say, 3 decimal places, round initially to 5 decimal places. This will ensure as much accuracy as possible. And then, of course, I added these two together. Oop, that's a mistake. Took the natural log of both sides and then divided, and I got 12.12 years. All right, so we have the half-life of a radioactive substance is 14 days. There are 6.6 grams present initially. How many grams will remain after? So this is half-life. If you've done chemistry or physics, you may have done half-life formulas before. We'll still use P as our principal, but this time it's 1/2 to the power of T divided by H. Make that more prominent, H. So our principal, the starting amount, 6.6 times 1/2. Now the half-life is 14 days. That is H, okay? So that's going in the fraction, 14 and then 150 days. Basically, this exponent is saying how many 14-day sections can come out of 150. Now, if you insist on entering this all into your calculator, make sure you put this little division in the exponent in parentheses. Some of your calculators may actually kick it up to an exponent, in which case that's okay, but not everyone does. So be sure, play it safe, put parentheses around it. That's 6.6 times 1/2. You can use 0.5. That's fine. 100 to the power of 150 divided by 14 is 0.0039. So we have 0.0039 grams, that would be, let's see, tenths, hundredths, 39 thousandths of a gram. And so we have the half-life on this next problem. Go ahead and give this one a shot. So again, using our half-life formula, we have 3.5 grams. Half-life, and then it's 250 divided by 65 gives us 2,434 10,000ths of a gram. All right, last problem. Let's discuss setting up logistical functions. Okay, so the general formula for that was I used C up here divided by 1 plus A times B to the power of X. Okay, now the limit growth right here, this is your C value. So we're going to plug that in right away. We have 40 divided by 1 plus A times B to the power X. Now, there's some logic we can use to find A, and then we can work backwards to find B. But I'm actually going to show you how to find them both working backwards. Let's find the initial value. Remember that your initial value is your y-intercept. This is when X equals 0. So we're going to plug in 10 for our big A. Okay. 1 plus A times B to the power of 0. That's when X equals 0. Now, anything to the power of 0 is 1, so we're just going to cross that off. We get 10 equals 40 divided by 1 plus A. And then we're going to go ahead and simplify our fraction. I'm going to multiply by 1 plus A to both sides. I am not going to multiply and distribute my 10. I'm just going to write it as 10 times 1 plus A equals 40. And then I'm going to divide by 10. All right, so cancel this out. I'm going to write 1 plus A is equal to, I'm going to write it out as 40 over 10 because I want to show you this little algebraic shortcut we can use. We started off with 10 equals 40 over 1 plus A. Okay, now we're at 1 plus A equals 40 over 10. We effectively switch the 10 and the 1 plus A. That is an algebraic shortcut you can use here. And we do get 4, of course. And then we subtract 1. So that gives us a little a of 3. All right, now we got to solve for b. So I'm going to rewrite the formula over here. I'm going to use a different color. So we got 40 up top. We have 1 plus 3 times b to the power of x. And now we're going to use this point right here to find out what our b is. So 20 goes in for big A. We got 40 over 1 plus 3 times b to the first power. Now, I'm going to use that algebraic trick since I don't have much space here to switch these two. So that's 1 plus 3b, b to the first is just b, equals 40 divided by 20, which is 2. And then it just becomes a matter of solving. We got 3b equals 1 divided by 3. We got b equals 1/3, but also notice that could also be 3 to the negative first. Okay, you can write it however you want. So let's write our final answer. We have big A equals 40 up top. Okay, 1 plus our A is 3, and then our B is 1/3 the power of x. And we're done. Go ahead and give this last problem a chance as an exit ticket. Thanks for watching.